Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Assa. I want to discuss with you what we see right here: rapid acidification of the Arctic Chukchi Sea waters driven by anthropogenic forcing and biological carbon recycling. Now, this is a lengthy paper with a lot of um, detail to methodology, uh, the development of the mathematical analytical tools that they use, translation, a lot of vector calculus. so, so it gets really in the weeds there. I will leave the URL in the comments section for those who are interested in. But what I want to discuss with you, what I want to share with you are the major findings and what it means. So before I look at the abstracts, let's look at the introduction. Since the Industrial Revolution, the decrease of pH and carbonate saturation state, omega, caused by ocean uptake of anthropogenic CO2 from the atmosphere, namely ocean acidification, here referred to as OA, has become an important environmental issue that seriously threatens the marine ecosystem healthy and the development of human communities. It has been widely observed that the long-term ocean acidification rates are comparable to the rates predicted from the increase of atmospheric CO2 across the global oceans. However, for the coastal oceans, so when they're talking about global oceans, they're talking about more pelagic region, open water, over deep, like over the shelves and basins kind of stuff, as opposed to over the slopes as opposed to the shelves. So here they're looking at the shelves. A lot of other studies that looked at the slopes and the basin. However, for the coastal oceans, observation-based assessment of ocean acidification and its driving mechanisms is limited due to the complexity of intertwined factors, including anthropogenic forcing, natural variability, and local biogeochemical processes. Atmospheric circulation, mixing of water masses, biogeochemical signals mitigate or amplify the atmospheric CO2 increase induce ocean acidification. Therefore, it is difficult to decipher, validate ocean acidification with robust evidence. Across the global oceans, the Arctic Ocean has a strong CO2 absorption capacity due to its low temperature. How many times have you heard me say that decreased temperature, increased gas solubility, and vice versa? Both observations and models have shown that the ice-free Arctic Ocean is the most susceptible region to ocean acidification and that it would be the first ocean basin to encounter severe undersaturation of aragonite calcium carbonate, basically referred to as omega or rag, less than 1, probably micromoles. But here's the interesting thing: we know about ocean acidification, for example, and what it does to corals, like coral bleaching, etc. And as bad as that is, what they're basically implying is that there could be even increased acidification in colder waters because of the capacity to hold more CO2. And if you have the capacity to hold more CO2, you're going to basically not reach saturation levels. It's kind of interesting. Chukchi Sea, as an important inflow continental shelf of the Arctic Ocean, has experienced more dramatic climate-driven changes, rapid sea ice retreat, and increased inflow of nutrient-rich surface water from the Pacific Ocean. Rebecca Woodgate, right, her crew there, resulted in an increase in primary production, and the increase in carbon sink accounting for more than 50% of the overall Arctic Ocean CO2 sink, 8% of the global marginal sea CO2 sink. Sea ice loss also has substantial impact on ocean acidification as it experiences extended ice-free periods during summers, which allows for more absorption of the gas from the atmosphere. When you got ice on there, well, any CO2 in the atmosphere is not going to go into the water because the ice is blocking it. It's a cap. The emerging ice melt promotes primary production and CO2 removal. That's called ice edge productivity, which is a major contributor to productivity in the Arctic Ocean. Okay, so that keeps the high ocean acidification buffer capacity and oversaturated. In other words, less likely to increase dissolved CO2. In the surface mix layer, meanwhile, ice melt is sometimes accompanied by the dissolution of calcium carbonate trapped in sea ice, which then consumes the CO2 and alleviates acidification. Although the concentration of the soluble calcium carbonate is possibly low in sea ice, 2 to 4 micromoles per liter, the dissolution of calcium carbonate would increase TA and also the CO2 buffering capacity. Let's see, did they identify what they mean by TA? Total alkalinity. Okay. So TA is increasing alkalinity. If you're increasing alkalinity, that means you're reducing acidity, which means you're improving the buffering capacity. And therefore, if you do that, you actually set up a system where you can actually enhance atmospheric CO2 uptake. On the contrary, sea ice melt removes the barrier to air-sea gas exchange and promotes the uptake from the atmosphere, which potentially lowers surface pH and the aragonite concentration. In addition, increased microbial decay of organic matters in autumn and winter can strengthen the seasonal acidification by releasing CO2 into the subsurface and bottom waters. In particular, close to 40% of the shelf bottom water was subject to aragonite of less than 1, and about 80% of the shelf bottom water was subject to aragonite of less than 1.5. Basically, this is just a dimensionless number in which they're using 1 as a reference, where 1 in particular means that you're going to increase the acidity, decrease the pH. 1 is about neutral, it stays about pH of 7 basically, and then greater than 1 is you're increasing the alkalinity. That's kind of what they're getting at there. On a decadal scale, the long-term oceanic acidification trend in the Chukchi Sea can be attributed to a combination of several processes, including those increasing acidity, cooling-driven increased CO2 solubility in atmosphere, CO2 uptake, and CO2 release from respiration, and those decreasing acidity, warming-driven decreased CO2 solubility and CO2 outgassing. Photosynthesis, which utilizes CO2, and dilution by sea ice melt water and river water. Okay, let's pause there for a moment. So basically, colder waters, you can draw down more CO2, increasing the acidity. Okay? And also you have organisms releasing CO2 due to respiration. But if you have warming waters, well, warmer waters holds less, the gas solubility decreases, so you decrease the CO2 solubility, but then that leads to CO2 outgassing. So it's like, which one do you want, right? And we know that the Arctic Ocean is warming. We also know the flow is increasing. So generally you would expect if the Arctic Oceans continue to warm, you would expect the pH to increase, i.e. the acidity to decrease, but then that CO2 possibly could outgas to the atmosphere. And they go on to say that the long-term trends need to be better understood. So what do they say in the abstract? The acidification of coastal waters is distinguished from the open ocean because of much stronger synergistic effect between anthropogenic forcing and local biogeochemical processes. However, ocean acidification research is still rather limited in polar coastal oceans. Here we present a 17-year, from 2002 to 2019, observational data set in the Chukchi Sea to determine the long-term changes in pH and aragonite saturation state. We found that pH and the aragonite saturation state declined in different water masses with average rates of minus 0.0047 plus or minus 0.0026 per year, and minus 0.017 plus or minus 0.009 per year, respectively, and are about 2 to 3 times faster than those solely due to increasing atmospheric CO2. We attributed the rapid acidification to the increased dissolved inorganic carbon owing to a combination of ice melt-induced increased atmospheric CO2 invasion and subsurface remineralization induced by a stronger surface biological production as a result of the increased inflow of the nutrient-rich Pacific water. So, what's the plain language summary? Anthropogenic CO2 absorbed by the ocean leads to a lower pH and a calcium carbonate saturation state and threatens the marine ecosystem state of healthiness via a process called ocean acidification. The Arctic Ocean is particularly sensitive to ocean acidification because more CO2 can be dissolved in cold water. This study used the observations collected over 17 years to estimate the long-term trends of the aragonite and pH. The results showed that rapid acidification occurred throughout all water masses from 2002 to 2019, leading to or approaching aragonite under saturation. This rapid acidification is attributed to the enhanced increasing concentration of dissolved inorganic carbon, while sea ice melt induced uptake of anthropogenic CO2 partly explains the long-term acidification. The remainder is due to the increased nutrient-rich Pacific inflow water, which promotes high biological CO2 utilization in the surface water, but leads to stronger subsurface acidification due to regenerated CO2. That's basically a reference to the CO2 created by respiration from secondary and tertiary producers, etc. We suggest that the acidity in the Chukchi Arctic shelf waters will increase in the future if the increased inflow of Pacific water continues. So this is really interesting. You would expect when you have normal cold water, you can absorb more CO2, you increase the acidity. But we know what? That the Arctic oceans are warming. So that you would expect that to not absorb as much CO2, and therefore the acidity would decrease, not increase, it would decrease. But what they're saying is now we got this inflow of nutrient-rich Pacific water that helps increase productivity. And by the various biochemical processes involved with productivity, it's actually promoting increased levels of CO2, which then decreases the pH, increases the acidity. So now this is kind of interesting because generally in the Arctic Ocean, you have several sources of productivity. One, you have as the ice melts, you have ice edge productivity. Okay? You also have, if there's no snow cover on the sea ice, you have algae growing on the underside of the ice, and you have productivity from that source. Then, as the ice melts back, and then the sun gets high enough in the sky, you then activate the diatoms and the productivity resulting from the diatom. So you have those three sources of productivity. Well, losing the sea ice, you're kind of losing the ice edge productivity and the productivity from the algae on the underside. So the expectation would be, because you don't have a long period from when the sun is at a sufficiently high angle in the sky to promote diatom productivity, you would expect overall productivity to be less than what we have seen in the past. Well, now the question I have is, if this inflow of Pacific water that has a high level of nutrients, to what extent does that offset the decrease in productivity from algae and ice edge processes? That would be an interesting question to have answered. Does it does it offset it on a one-to-one, or does it perhaps, it does contribute some productivity, but overall the productivity is still lesser than historically was happened? That remains to be seen. But that is an interesting thing to see. And I think I saw a recent paper that kind of looked at that. I got to go find it now, and then maybe I'll discuss that. But this is kind of interesting. It's the ocean acidification issue, of water plus CO2 making carbonic acid, and what that does to the organisms, and what this does to the pH of the water, etc. I've discussed with you before in quite a few videos. The general process, the general implications. Like for example, the lysocline, the calcite compensation depth. That'll be another interesting thing. They did not really address the CCD in this paper here, but it'll be interesting to see what that does to the CCD. Does it go shallower or deeper? How does that tie into how the halocline is changing? So there's all sorts of interesting interconnections that could take place here. So generally speaking, colder water, more CO2, but the Arctic Ocean is warming, so less CO2 in the water, but more stays in the atmosphere. So, okay, so you don't make the oceans as acidic, but then you have the increased inflow from the Pacific, which could promote more productivity, which then might, in essence, make the oceans more acidic. Almost like no matter what you do, the acidity is going to increase. So, as I said, I will leave the URL in the comment section for those who are interested. But I thought this was kind of an interesting finding, and I wanted to share with you some of my thoughts on that. Thank you for your time. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.